Okay, so energy and chemical change. We can change energy from one form to another. So for example, if you had like a coal burning plant, the coal has energy stored in the coal, in the bonds of that coal, and they go in and they're going to burn that coal, which then heats up this water. So heat energy is getting transferred from a chemical bond into heat. And then that heat is then being transformed into mechanical energy over here in the generator, which is then transferred into electrical energy to your house, which then might transfer another, engine or motor or something like that that turns, like in your blender or your mixer or something, hair dryer or something like that, which then your hair dryer would also generate it as heat. So energy can change forms. And I was, this lecture is like 55 slides long, but we're not going to get to all of them this year. Normally I would get to that whole section and talk about some of that energy transformation and how much energy is stored in the bonds and how we tell that and everything, but it's just not going to happen this year. So, but one of the things that we need to absolutely have down before you guys come back to me in AP is this idea of specific heat and how to do those types of equations, which is also applicable to physics. Sometimes they talk about that in physics as well. So kind of double dips both areas. All right, law of conservation of energy says that any chemical reaction or physical process, energy can be converted from one form to another, but it's neither created nor destroyed. So we're converting it, and sometimes it's like converted into like friction force, which, you would see that in physics, and they'll talk about friction a lot in there. Chemical potential energy is the energy that's stored in a substance because of its composition. Chemical potential energy is important for chemical reactions. Heat is energy that is in the process of flowing. It flows from a warm object to a cold object. Heat goes from a warm to a cold. So when your mom is yelling at you because you've got the front door open in the winter, and she's like, "You're letting the cold air in." You're not letting the cold air in. You're letting the heat out. Don't correct her. She'll probably backhand you. Okay? But heat moves from warm to cold, not vice versa. We use this little Q to represent heat. We can measure the energy that's in bonds through something called calories, and you'll see this on your food. Okay, the energy content of food is measured in calories. There's 1,000 calories with a little k in a calorie with a big K. Or not K, a big C. So calorie with a little c, there's 1,000 of those in a calorie with a big C. The stuff that's on your food labels when you get food, so I got like my yogurt here. Okay, so on my food here, it says that this is 80 calories with a big C. Okay, and this is all that's on your, but actually it's 80,000 calories per cup of yogurt. Okay, when we're talking about like energy in here. A joule then is equal to this many calories. Little c. Now, why don't they use the little c on stuff? Because there would be just too many numbers. Okay, it's just too big. So that's why they do it in kilocalories. Okay, so here's kind of a relationship. You've got this chart in your notes. 1 calorie equals 1 kilocalorie. 1 calorie equals this many joules. And that's what we typically will measure heat in. And that's what they will in physics. They're going to be all about the joule. And then 1 joule equals this many calories. Okay, so we've got breakfast cereal, orange juice, and milk. We have 230 calories with the big C. How many joules is that? Figure it out. Use your dimensional analysis and those conversion factors to figure it out. want me right now. There we go. Okay. Nope. Nope. There we go. Now it's gotten over itself. Two, 3, 9. 2, 3, 9. All right. Okay. Throw that in my calculator if I can find it. Ooh, that's a big number. Did you get a big number?
I got a really big number.
Okay. So 962,343. That's going to be joules. Okay, did you get that on your calculator? Good. Good? Good? All right. Easy enough? All right, specific heat of any substance is the amount of heat required to raise 1 gram of that 1 degree Celsius. So we're back to the land of Celsius now. Okay, we were in the land of Kelvin, now we're coming back to Celsius. Some objects require more heat than others to raise their temperature. I mean, think about like if you had a pan on the stove and it didn't have anything in it, right? You got a metal pan there, you turn on the burner. It doesn't take long for that metal pan to heat up, right? Now, you put water in that pan, you put 2 or 3 cups of water in that pan, and you give it that same amount of time, the water doesn't even feel like it's warmed up yet, okay? Water has a much higher specific heat than the metal does, okay? Certain things heat up faster and cool down faster, and that's this idea of specific heat. Water has a very high specific heat, okay? So here's water. Here's some of your metals. You can see just kind of the scale of that. This is 4.184. You go down to like iron. So you got a cast iron pan, for example, it's 0.449. So you can see that, as you move around here, an aluminum pan, it's 0.8. This is like 10 times more specific heat than this guy. So it's going to take a lot longer to heat up that mass, okay? So this is our formula that we're going to be working with. Q is the amount of heat that's either absorbed or released. C is that value for specific heat. M is the mass of the sample, and then delta T is how much the temperature has changed. Okay? This doesn't switch for me. So temperature of a sample of iron. We've got a mass here, it's changed from this, and it's releasing this. They want to know the specific heat. So the formula here is Q equals CM delta T. So your Q value is this. Your specific heat is what you're solving for. And then your mass is here. And your delta T you get by subtracting these. So see if you can figure out what that's going to be. Get it?
I think so.
How does it compare to what iron should be on that chart?
Pretty close.
Good?
Yeah.
All right, so it's going from 50 degrees to 25. So this is your initial, this is your final temperature. So your delta T should have come in at minus 25.4. And then you're going to multiply that by 10. And you're solving for C. That's going to equal 114. Okay? So I'm going to divide 114 by 254 negative. So my C, or actually, no, I shouldn't do a negative there, should I? Because we don't have a negative specific heat. We'll just leave that as a positive. It's fine. Oh, because this would have been a negative. That's why. And this would have been a negative. So yeah, that makes sense. So this would have been a minus, and then this would have been a minus. There. And then the minuses cancel out, giving you a positive specific heat of 0.449. Okay? Did you get that?
Yeah, it was the same.
Huh?
Yeah, it was the same.
Okay, good. All right. So that's our sample problem. You're going to be doing specific heat problems tonight in your notes. And then tomorrow, I think that's all we have to do for specific heat tonight, right? Yeah. And then tomorrow we'll talk about calorimetry and how to do calorimetry. So I'm going to give you both worksheets, and then the other one you'll watch the lecture tomorrow on, and then do that lecture. These are the last two assignments for the year, and then you've got a specific heat lab that you'll be doing when you come back to me on Thursday. And that'll be your last assigned item for the year. Everything is due on Friday. Okay? You guys are not here on Friday?
No.
So make sure you get it turned in Thursday or come and visit me on Friday. All right, I'm not taking, the only thing that I'm taking after Friday is that specific heat lab. And the reason why I'm not is because y'all aren't here. You know, that's the last day. So that's the only thing from you guys that I'm taking. So make sure that you have everything that, you know, all your makeup work, all of that stuff is taken care of before you come back to me on Thursday if you're not going to come in and spend some extra time Friday. Okay?
Wait, why are the numbers negative again up there?
Because it's being released
Okay, that's why.
and the temperature went down.